Welcome to Modeling Circular Motion. We're going to take what we learned in the last lesson about trig functions and use that to help us to track the position of a point on the circumference of a circular object. Ferris wheels are circular and rotate about the center. The spokes are radii and the seats are points on the circumference. So try to picture that, and then let's describe this motion in terms of what happens to the x and y coordinate of the red seat, for example. We want to find angles of rotation between 0 and a 360 degrees once around that will take the red seat from point A to the following special points. So point A, I'll mark it on this lower circle down here, is right here. This is our point A. We want to determine the maximum and minimum distance from the horizontal axes, the max and min from the vertical axes, and then try to find points with equal x and y coordinates. In other words, they're the same, and then points with opposite x and y coordinates. In other words, they have opposite signs. Pause the video and see if you can think about where those points might be. Part A, the maximum distance from the horizontal axes. Well, our horizontal axis is our x. So to get as far away as possible, we'd have to be up here at 90 degrees or down here at 270 degrees. Those would be our max distances. To find our minimum distance, we would have to be on the x-axis. That way we're not away from it. So it would have to be here where A is at 0 degrees, or we could call that 360 degrees if we went around one full time, or over here at 180 degrees. Both those coordinates or angles would be a minimum distance from the horizontal axes. How about the vertical axes? Well, in order to get away from the vertical axes, we would need to be as far to the right as possible. So in other words, right here at A again, we would be very far from the vertical axes. So again, at 0 degrees or 360 degrees, we would be at our maximum. Or over here to the left, this would then become our maximum away from our vertical. Whereas at 90 or 270 down here, we would be on the vertical axes, so we would be at a minimum. How about points with equal x and y coordinates? Well, if you remember way back to Algebra 1, a 45-degree slope is a 1-to-1 relationship, which means that for every amount you go out on the x, whatever that distance is, you go the same distance up for y. In other words, these points, x and y, will be the same. They'll also be the same sign. So if we split 0 and 90 degrees, this would be at 45 degrees. Can you think of another point where our coordinates would be the same? Well, hopefully you're thinking down here. It wouldn't be in quadrant 2 because our x is negative in quadrant 2 and our y is positive. In quadrant 3, both the x and the y coordinates are negative, so our x and y would be the same. Well, what is that degree? We know that if we go all the way around halfway, that's 180. Plus, we went down an additional 45 degrees. That means that this point right here is 225-degree rotation. Now what about quadrant 4? We wouldn't have one in quadrant 4 because while x is positive, we would have to drop down for y and that would be negative. So those would not be equal. What about points with opposite? Well, we know now that if we split the angle in half, our x and y are the same. So right here, we would have a situation where x was negative, y was positive, but our actual values are the same. So what is that? Well, 90 plus 45 would be 135 degrees right here. And then down here, we would have another one where they were opposite. To figure out that one, we would come all the way around to 270 here, add 35 to that, and we would get 315 degrees. And that's one way to think about where this red seat is in location to our coordinate plane. When a circle like that we just looked at, modeling the Ferris wheel, is placed on a rectangular coordinate grid with the center at the origin, 0, 0, we can use what we know about the geometry and trigonometry functions to find the x and y coordinates of any point on a circle. And that's what we're going to look at right now. Remember this from the prior lesson. We said that the sine of theta in the coordinate plane is opposite over hypotenuse, or r. Well, what if we want to know what this y-coordinate is, the exact value, or the exact value of the x-coordinate? Well, what we can do is we can take these functions and we can just solve for x and y. In order to solve for y, we would just multiply both sides by r in order for the r to cancel out. And we would be left with an equation of r, which is our radius, times the sine of the theta, or the angle right there. That would be y. We would do the same thing for cosine. We could multiply both sides by r in order to eliminate the r from the right side. And we would be left with r times the cosine of theta, and that would be our x-coordinate. Now, if r is equal to 1, then 1 times the sine of anything is just going to be the sine, and 1 times the cosine of anything is just going to be the cosine. So we can define x as cosine theta and y as sine theta, assuming that our radius is 1. Let's try a few of these examples together. In this example, we want to find the coordinates of a point that tell the location of the Ferris wheel seat that begins at point A, which is at 1, 0. 1, 0 then is right here, meaning that our radius, the distance from the center to the circumference, is 1. So if we take our equations, 1 times the cosine of theta and 1 times the sine of theta would just give us cosine theta and sine theta. And that is what we are going to use to find the coordinates of our seat at these different angles. So let's go ahead and set this up and try a few. I've gone ahead and written out the first 3. So for a 30-degree angle, we want to know how far out for x and how far up is our seat. What are our coordinates right here? Well, remember that to find x, we just take the cosine of our theta, and our theta is 30 degrees, and the sine of our theta. Let's give that a try. 30 cosine gives us, let's clear that out, 30 cosine gives us 0.87. And then let's look at our sine. So 30, and then I hit sine, gives us a half, or 0.5. So that means that we traveled 0.87 feet or meters this direction and 0.5 up to get us at that exact value. Let's look at the cosine and sine of 45 to see what point that would be. Remember too that we thought that at 45 degrees, where this blue line is drawn, our x and y coordinates would probably be about the same. So let's check. 45 cosine is 0.7 and 45 sine is also 0.7. So in fact, our coordinates right here are 0.7, 0.7. They are the same. Let's look at 90 degrees. With 90 degrees, we really don't need to plug this into a calculator because we know that the x coordinate right here is 0 and the y coordinate is 1 because our unit out to the circumference is 1. How about 120 degrees? 120 degrees is about right here where this green line is. So it's 90 to here plus another 30 to there for 120 degrees. Now let's think about these coordinates. When I put these in my calculator, I know that my x coordinate should be negative because I'm going to the left, but my y coordinate will still be positive. So let's make sure that's the case. 120 cosine gives me negative a half, or a negative 0.5. And 120 sine gives me 0.87. So my coordinates here are negative 0.5 and 0.87. Look familiar to this one? Remember, this is 30 degrees. 120 is a multiple of 30 degrees. That is something interesting to think about. Now let's go ahead and look at the theta of 315. That's going to be about right here where this blue line is. So that's in quadrant 4. So what should our coordinates be? Well, our x-coordinate should be positive, but our y-coordinate in this case should be negative. So let's try this out. 315 cosine gives us 0.7, and 315 sine gives us negative 0.7. So, that should be positive. So our x-coordinate came out as positive 0.7 and our y-coordinate came out as negative 0.7, which is what it should be here. Now notice that these coordinates look like these coordinates here. That was at 45 degrees. Well, 315 here is really just 45 degrees, but going in the opposite direction from 360. So if you take 360 and subtract 45, we get down here. So again, interesting that the coordinates are the same. For the last one, let's look at 180. Again, we don't need our calculator for this one because we know the coordinates here. For x, that's -1, and for y, that's 0. Likewise, we can find the coordinates here at 270. For x, we're at 0, and at y, we're at -1. So all these calculations we were able to find in our calculator. Now remember, this is a unit circle, meaning that from the origin out to the circumference, it's only 1 unit, whatever that unit might be, 1 mile, 1 meter, 1 inch. If, on the other hand, our radius had been 5, then for each of these numbers, we would need to multiply by 5. Because remember, if we go back and we look at our calculations, really, our answer is the radius times the sine of theta for y, and the radius times the cosine of theta for x. So in all these cases, if we'd had a different radius, we would have had to multiply, for example, -1 and 0 times 5 for each. So just keep in mind that we were able to just use the cosine of 30 for x and the sine of 30, for example, for y, because our radius was 1. This concludes our lesson today on modeling circular motion. So now you ought to be able to take a unit circle and locate any one of these points, the location, anywhere on the coordinate plane, using your sine and cosine functions.